a wave function, an eigenstate, a solution to your Schrodinger equation, un, and an energy, an eigenvalue, en. And this en here is just symbolic. What it really is it's E minus n. So n is the integer. That n is the number of times that you've stepped down. Okay? Right? Now, so this energy is going down by 1 unit each time you step down. So that implies, if you think about it, that implies that the allowed energy levels are stepping down evenly. You know, they're going down. Now it's E, right? This this eta thing, which is the original eigenvalue in your Schrodinger equation, divided by h bar omega. So it's in this E. If it's going down by 1 each time, in terms of your original energy E, that energy E is going down by a unit value of h bar omega, right? So each time you step down, the allowed energy is decreasing, stepping down, decreasing by h bar omega, right? So the allowed energy levels are spaced evenly, right? And the difference between the energy level each time is h bar omega, right? That just comes out of this, all right? Okay, so if we know the initial energy, so if we know, like, if we had to start somewhere, right? If you're going to step down, we're stepping down relative to some starting position. So we need some starting energy, and we need some starting u, some initial eigenstate, some initial wave function u, and then we can, by stepping down, in other words, here, like here. So if you start with a u, you step down with this operator, you get a new solution, a new wave function, a new eigenstate, and all the same thing. Right? U dashed, right? And if you want to get another one, well, you just you apply a minus to u dashed, so you get like u double dashed, and so on, right? So you can just keep going down, down, down. The energy keeps going down, and you keep getting these new eigenstates, right? That correspond to whose eigenvalue, in other words, the energy, allowed energy, keeps going down by a unit of h bar omega, right? Right? So. So once you have like some starting wave function, you can generate all the lower ones by finding what's like u dashed, u dash dashed, u n dashed, from this, by using this idea. Right? You keep applying the a minus to your u, and then your a minus that result, and then you a minus the result of the result, and so on. Okay? Now, but you cannot continue doing this forever, okay? Because we're talking about the simple harmonic oscillator. We know that there is a ground state energy. There is like the ground floor energy level, the lowest possible energy level, and we know that that's a half h bar omega, right? So we cannot keep stepping down forever. Right? Sooner or later, it will have to stop. Now, have a look at this equation with a triangle. Where is it? Here. Have a look at this. Now, one. Well, maybe this one. Yeah. So this is just the same as this. Right? It's just rewritten in different symbols, but so this is just the same as that. Now have a look at this. One simple solution to this is u dashed is 0, right? if you apply this operator A plus, where is it? A plus. So d per dz minus z. If you apply that to 0, well, 0 is a constant, right? So if you differentiate a constant, you get nothing. And z times nothing, whatever z is, still nothing, right? So if u dash is 0 here, that's a solution to this equation. And therefore, that u dash is a solution to this. See, this and this, they're equivalent, right? So if u dash is a solution to this equation, u dashed is a solution to this equation. So it's a solution to your Schrödinger equation. So you found one, right? So let u dashed be 0. So that means a minus of u is 0. Right? I mean, you can't keep stepping down forever. Because each time you step down, that your energy level lowers by an amount h bar omega, but you know the ground state energy level is half h bar omega. So that's the limit. That's the lowest possible energy. That's why it's called the ground state energy. Like ground level, bottom. All right. Okay. So you use u dash. Let that be 0, and so let this u dash correspond to the ground state, the lowest energy level state, wave function. When I say state, state, wave function, eigenfunction, all the same, pretty much. All right. Okay, so if u dash is 0, let that be your lowest level. U dash is 0, but u dash by definition is a minus u naught. From here. Yeah, so let that correspond to the well, we've got the eigenstate at the lowest possible value before it's 0, right? So that's the first state that becomes 0 as you lower your eigenstate, your state of lowest energy, u naught, right? And we've let that be 0. But a minus is just this, d per dz plus z, a minus, so it's d per dz plus z, okay, from here. And a dashed is naught, so all that has to be naught. Well, so du naught dz plus zu is 0. Now you can solve that fairly readily. So you get u naught is some constant e to the minus z squared over 2. Now we've seen that result before, right? So we've now got a formula for the wave function, the eigenstate, eigenfunction, same thing, at ground level, u0. It's of this form. So we've got the same result that we got before using the Hermite polynomial technique, right? Now, in a sense, and this is like you're getting a foretaste for what's to come, higher level quantum mechanics. In a sense, you can say this u dashed, like here, when this operator, the a minus, the step down operator, when that step down operator applies to u minus, you get 0. So in a sense, applying this operator a minus kills or annihilates this state, right? So in a sense, you can say that this u naught here is annihilated by a minus, because when you apply this a minus to that state, you get nothing, u dashed, you get, all right? So a minus u naught is just 0. Now, if that's the case, have a look at this equation here, with the asterisk star. So this equation here. Now, if a naught u naught is 0, let's assume the eigenstate u0 is not 0, right? It's just the lowest eigenstate. So we assume that u naught. So u naught, a minus u naught is 0. So left hand side is 0, and u naught here and we assume u naught is non-zero. So that means this has to be 0. Okay, so that means that e at eta epsilon whatever, this e here has to equal a half, right? So this eta has to be a half. So from here, if that's a half, that means your original eigenvalue from your Schrodinger equation, capital E, equals a half